Thermal conductivity of combined conducting rods. Say I'm having a kind of a thermal conductor like a metal rod here. If this is a single conducting rod, then how much heat that would pass from this end to this end? For this, I have to specify many other parameters. If Q is the heat energy that passes from this end to this end is hotter end and this is the cold. It is cold with respect to this. Okay, so now the length of this rod is L. This is L, and area of cross section of the rod is A. And now the heat which is transferring from here to here in time T, okay, heat is transferring from this end to this end in time T, and also I have to specify the temperatures. The hot temperature is say theta and cold temperature say theta O. If I know all these parameters, now I can easily write the rate of heat flow. Okay, the rate of heat flow. Rate of heat flow through the rod is Q divided by T, which is equals conductivity of the rod. Okay, the conductivity of the rod is K. If I say it is K, it is multiplied by A, which is area, and it should be divided by the length and multiplied by the difference in the temperatures at the ends. Okay, so this much I can say. This is the expression what we use to define thermal conductivity. Moreover, I have to tell you the information that this Q by T is called heat current. This is called heat current. How much heat that passes through the conductor in unit time, that is Q by T, right? Otherwise we call it watt. Okay, so this is the temperature difference, theta minus theta 1 divided by L. If I combine these things together, this is a heat gradient or temperature gradient, I may say, temperature gradient. More the temperature gradient, more will be the heat current. Right. So if the temperature difference is a lot, then the flow of heat will be more. Okay. So now if you think the rate of heat flow, it will be more when there is larger area. It will be more if the length of the conductor is less. Otherwise we can simply say the unit of K, the SI unit of K, what it becomes, it is watt, right? Watt divided by meter. Okay, this is per degree Celsius, otherwise Kelvin in SI. So it is watt per meter per Kelvin. That means in 1 meter length, how much power will be carried per unit difference in temperature. This is how you have to understand the term thermal conductivity. Now we have to say it for the combination of such rods. Okay, the combination of such rods. For example, if I am having two rods connected like this, I simply assume such a kind of one square rod is connected here. This is such a kind of one rod, and one more rod we are connecting in the bottom. So this. Okay, so this is how we connected. right? This is the way how we connect. And now the total length of this rod is L. The combination itself is L. I am assuming the length of two rods are same. Here is one area and here is one more area, right? The two areas when combined, okay, so it's on that side also, right? So these areas are 2A, because here in the first picture I shown you, this small area, if I consider A, and the combination will give us a area double. And further one rod will carry a heat, say it is a Q1, okay, so Q1, which is a heat in a first rod, and second rod carries another heat energy, that is Q2 in the same time, okay, in time t. I assume again one more thing, that is the temperature on this side is theta and on this side it is theta O. Okay, the temperature difference is theta and theta O. Theta is here and theta O is on this side. And now again, if we want to find out the rate of heat in first rod, okay, in first, what I can write, it is Q1 divided by T is equals, the first rod is of conductivity, say it is K1, so I can write K1 into area, first area is A, right, divide by what is the length is L itself, and what is the temperature difference, it is again theta minus theta O. And for the second rod, I can write Q2 divided by T is equals K2 into A divided by L, again theta minus theta O. Okay, so now the combination, if I think it as the combination, the total heat that flows, okay, then the combination, for the combination what I can consider is the net flow is simply like this. Okay, this is the combination. If I call this is the combination of both the things, both the rods together as a single piece. Okay, so this is again of length L, and this area what I written, it is 2A. It is on this side also, right, this side also, and this temperature difference is one more time the same, which is theta and theta O. The heat flow will be taken as Q. What is Q actually? Q is the net flow of heat. Now when you combine this effect here, right, what equation I can write here? So the equation will be, it is Q divided by T is equals, in the same time, right, in time T, Q by T is equals the effective conductivity, say it is Ke, the area is 2A, divided by the length is L, and the difference in temperature is theta minus theta O, right, theta minus theta O. Well, further what I can write is, in the single rod, the upper rod, the energy is Q1. In the bottom rod, the energy that flowing is Q2. The effect is Q1 plus Q2, the total. So that is equal to Q. Right. Now what I can write? I can write Q is equals, it is Q1 plus Q2. Otherwise I can write Q divided by T is equals Q1 divided by T plus Q2 divided by T. What I can write for Q1, which is just Q is this much, right, and Q2 is this much and Q1 is this much. If I put all these things here, definitely the common terms on both sides get cancelled, right. The remaining terms are, it is nothing but 2 times Ke, which is equals, this will be K1 and this is K2. Therefore, what it comes for Ke? Ke is K1 plus K2 whole divided by 2. This is the effective conductivity of the system of conductors as a whole. Further, I can show you what happens if you connect the two rods in series, one after the other. Well, the situation may go like this. Na? Here what I am writing is the two conductors are connected in this manner. Okay, so this is how we connect. Length may be anything, but for simplicity I simply assume both the rods are of same length. Okay, same length. And this area is A, this area is also A. The length is, one rod is of length L, another one is also L. What is the temperature that is existing? Let's say it is theta. Okay, it is theta. It is theta 1. It is theta O. Okay, so theta, theta 1 and theta O. Now, the heat that entering here is Q and which is leaving here is also Q. And the conductivities are K1 and K2. Okay, conductivities are K1 and K2. Now, what the expression I can write for the rate of heat flow in the first part of the conductor for this? Okay, the rate of flow of heat is, it is Q divided by T, right? It is K1, area is A and length is L. The temperature difference is theta minus theta 1. Meantime, I can write the rate of heat flow for this. Right, rate of heat flow will be Q divided by T is equals K2 into A divided by L into theta minus theta O, theta 1 and theta O. Right. So now what I have to rewrite here is, if I rewrite this equation in a different way, that is theta minus theta 1, which is equals L divided by K1A into Q divided by T, keeping this thing in bracket. Meantime here it is theta 1 minus theta O, which is equals L divided by K2A into Q divided by T. Okay, yeah, they like this. The term what you are seeing in the bracket is heat resistance of the conductor R. Okay, the bracket term is defined as heat resistance of the conductor. The symbol is R. How we can write R for both? Means heat resistance R1 for the first conductor is L divided by K1A, and for the second conductor is R2 is equals L divided by K2A. Okay, like this. When you combine these two as a single, what you are seeing like this, the effective combination will be treated like this. For the whole combination, what I can write? the heat flow remains same, whatever the heat that enters. Okay, whatever the heat that enters, that is living. Therefore, Q divided by T must be is equals K effective. K effective is the effect of these two conductors, the conductivity of those two conductors in effect as a combination. The area is simply A divided by the length should be treated as 2L. Right, the complete length should be treated as 2L. The temperature difference now should be written as theta minus theta O. Right, theta is here, theta O is here. So theta minus theta O. What I can write for the expression for heat resistance now? Heat resistance as effective is equals, it is 2L divided by Ke into A. Okay, so this is the expression for heat resistance of the conductor as the combination, and this is for the first and this is for the second. Now here the heat will be resisted by this conductor and after that by this conductor. That means in this situation the two conductors will act like the two resistors which are connected as in electricity. Okay, like this. This is the first resistor and this is the second resistor. And how actually we write the effective resistance between the ends? The effective resistance is R1 plus R2. Similarly, in this situation, here in the heat, we also consider the same, that is RE is equals R1 plus R2 in heat. So now put the things what we know about all these things. RE is 2L divided by KEA. It is 2L divided by KEA. What is R1? It is L divided by K1A here. What is R2? Which is L divided by K2A, which is here. Now when you observe this, L divided by A get cancelled on every side. Therefore, the things which are left behind are 2 divided by Ke is equals 1 divided by K1 plus 1 divided by K2. So in the next step I can rewrite 2 by Ke is K1 plus K2 divided by K1 K2. Finally I can write Ke is equals 2 times K1 K2 divided by K1 plus K2. This becomes the effective thermal conductivity of the two conductors which are connected in series. Okay, so this is the result, 2 K1 K2 divided by K1 plus K2.